Hello, my name is Ronik Fru. I'll be guiding you through the Networks and Infrastructure Fundamentals course at ITCA Osaka. Throughout this course, I'll be using the available books and labs provided by Osaka. I do assume you've already gone through this book. This recording is designed to emphasize on the key concepts that will help you gain a solid understanding of networks and infrastructure. My goal is to ensure that you get a thorough understanding of the essential topics and are well prepared to tackle the certification exam. This course is structured into 4 main chapters. As you can see, chapter 1, we'll be looking at connections and layers. Chapter 2, network architecture and components. Chapter 3, networking language. And chapter 4, network infrastructure. Every chapter begins with a learning objective, then its knowledge content structured into sections, as you can see, and then close out with knowledge check. Before I proceed with chapter 1, I'm going to take you to the appendix. Please take some time and get yourself acquainted with the key technologies and key terminologies for a better understanding of this course. You can use the flashcard. Let's get to business. After you complete this chapter, which is chapter 1 on connections and layers, you're expected to be able to arrange the layers of the OSI model correctly, differentiate between OSI and TCP/IP models, recognize physical connection media, deconstruct IP addresses, explain basic radio theory, and distinguish between wireless technologies. Let's begin with Open Systems Interconnection Model. The Open Systems Interconnection Model, it is a standard that was created by international organizations of standardization called, in other words, ISO. This was done in the late 1970s. Another thing for your understanding here is during this time, which was between the late 1960s to the late 1970s, there were a lot of organizations that were involved in developing standards. So a takeaway for you here is ISO, which is International Organization for Standardization. So it's responsible for the OSI model. The table in figure 1.1 shows the 7 layers in the OSI model layered in descending order from 7 to 1. You can see. There is a mnemonics that you can use to memorize this. You've got 2. One which takes you from layer 1 to layer 7. Please do not throw sausage pizza away. And the other one which takes you from a top down descending order. All people seem to need data processing. My preference is that please do not throw sausage pizza away, because by default data package moves from layer 1 right up to layer 7. The table in figure 1.2, it's still an OSI model, but then it contains information on every layer. The takeaway for you here is to focus on not only how the layer is layered in an orderly manner, but to be aware of what is content at every layer, the actions taken, and what the content is called. An example here is the layer 1, which is the physical layer. For instance, whatever is contained at that layer is a frame that is being passed. And that frame, the action is it's been put onto the wire. And the value or the name for it, it's in bits. Okay, we're gonna dive deeper a little bit into the 7 layers of the OSI model. Before we proceed with physical layer, which is the layer 1, I just want to call on your attention here. The OSI model's got 7 layers. Layer 1 right up to layer 3 is what we call the media layers. And from layer 4 up to the last layer, it's called the host layers. So, okay, let's begin with the physical layer. As we dive into the details of these layers, you want to keep this in mind. These are your areas of interest. You want to be able to identify their responsibilities or what their job is and the process or protocols that are involved. Okay, with layer 1, it is a media layer that's located at the physical network. It's local. Its main job is simple, right? It sends and receives data in bits. And these data are actually numerical values expressed in ones or zeros. The layer can access and understand communication from a wide range of network media types. So usually the use of a cable, like an Ethernet cable, or wireless transmission technologies like 2 Wi-Fi's or 2 routers that are communicating wirelessly. So each media type employs a specific protocol to describe the following. Yep. Appropriate bit patterns is very important. Means of encoding data into media signals. Attachment interface characteristics of the physical media. Like I mentioned earlier, right, the Ethernet is an example of a physical layer, the Ethernet cable. It's an example. And when we talk about Ethernet here, we're talking about the cable that is being used for physical network connection. So a lot of us here have seen this or either use it. So if you have a computer that is hot-wired onto a router, then that's been done with the use of an Ethernet cable. The Institute of Electrical and Electronics Engineer is the organization that is responsible for the 802 working group. We have a couple of tables down. I will begin with the table in Figure 1.3. The table in Figure 1.3 just simply give you a display of the working groups. The rows highlighted in green are those with active status. So you want to keep this in mind. So focused on this one. So they like the 802.1, 802.3 for Ethernet, 802.11 for wireless local area network, 802.15. Yep, you want to keep this one in mind too. Yep. So and that just goes. So the next two tables, which is the one on Figure 1.4 and the one on Figure 1.5, represents the following. The table on Figure 1.4 is a list of Ethernet standards, 802.3 Ethernet standards. Please just go through this and get yourself acquainted with these Ethernet standards. The table on Figure 1.5 on sub-working groups, it just gives you a list of Ethernet sub-working groups. So just get yourself acquainted with this. So read it. Before we dive into the data link layer, which is layer 2, you should keep in mind that the OSI model physical layer includes the following: electrical connector and cable specifications. Yeah, we talk about cables. It deals with cables. Electrical specification of transmission line signal level and impedance. We're gonna see this down in the other chapters how it's been used. Radio interface descriptions, which are electromagnetic spectrum, frequency allocation, specification of signal strengths, and analog bandwidth, modulation, line coding, bit synchronization, in synchronous serial communication circuit switching. Yep, so just keep this in mind. Okay, data link layer. It is also a media layer that is local and physical network. This has responsibilities. It ensures that messages are delivered to the proper device, translates messages from the layers above into bits for the physical layer to transmit, formats the message into data frames. Those are its responsibilities. It just ensures it just ensures that it is. So it translates, it formats. So keep that in mind. It also adds a customized header containing the hardware destination and source MAC and source address. So the table on figure 1.6 just kind of shows you how a data frame is packaged at this layer. Keep in mind how many bytes we've got at the preamble. The preamble has got 8 bytes. The destination address got 6 bytes. Source address has got 6 bytes. Length address got 2 bytes. Data fields got 46 to 1500 bytes. File sequence check fields got 4 bytes. So keep in mind, the number of bytes that are contained in this header or in this Ethernet frame. You can read this as well for a better understanding of this course. Okay, the two things you have to take note at the data link layer. The data link layer has got 2 sublayers. It's got the logical link control sublayer, and it's got the MAC sublayer. And MAC just simply means media access control sublayer. The roles of the sublayers are actually what makes the responsibility or makes all the responsibility of the data link layer. For instance, here the logical link control, right? It plays the role of the managing buffer between the executive upper layers and the shipping department lower layers. That's it. And the logical link control sublayer also manages timing and flow control, the connectionless and connection-oriented protocols for some protocol stacks. Okay, the MAC sublayer, which is the media access control sublayer. It basically builds frames from the ones and zeros that the physical layer picks up as a digital signal. The MAC sublayer checks the CRC to make sure nothing was damaged in transit. It also determines whether the hardware address matches. So this is kind of like something like it helps with error control, right? And just kind of make sure and says, hey, the package is in full, it's going, it's not been damaged, That's it. The MAC sublayer handles 3 media access types. Contention. You can read that to understand what contention stands for. Yeah, it says typically used in the Ethernet network that allows all devices to communicate at will. That's a brief definition for contention. So it helps, right, to avoid data collision. Yep. By giving that room for devices to communicate, it helps to prevent data collision. In case if 2 devices are talking simultaneously. Token passing. Yeah, it's used. It uses a token ring, fiber to the data interface, and attached resource computer networks. Yep. It does pooling. So in cases of large mainframe environments, right, it helps with that pooling. That pooling just helps. So it just and what exactly it is, right? Host a pool to find out if they need to transmit. Another piece on that data link control layer is it contains the wide area network protocols, which is described basically as waveframes, the way frames travel between systems on a single data link. And those protocols are designed to operate over dedicated point-to-point facilities, multi-point facilities based on dedicated facilities, multi-access switch services, for instance, frame relay. The table on Figure 1.7 shows the typical encapsulation standards for synchronous serial lines at the data link layer. So you can read through this and just to get a detailed understanding of this course. So okay, we're going to be looking at layer 3, the network layer. It is the last of the media layers, so just so you know. It is actually used in a host-to-host communication. Besides the other responsibilities that exist at the network layer, the main responsibility of the network layer is sending packets from the source network to the destination network. That's it. That's his main responsibility. At this layer, right, the transport layer does use the network connected interface of the network layer to provide the best end-to-end packet delivery services. So the transport layer actually benefits from the network layer by being able to use that interface that it's got with it to provide the best end-to-end packet delivery service. So keep that in mind. The main responsibility of the network layer and how does the transport layer uses the network layer. So routing protocols use the addresses to pass packets from their sources to their destination. Look at the sample network map. We've got 3 routers on here, and every router's got an IP address on the various edges. So this is the IP address for this 10.10, the 20.2 for this, and that one. So that's just to give you a feeling of how it looks like that there. And for your awareness, routers operate at layer 3, which is the network layer. That's why we start seeing and talking about routers and IP addresses. Just for an understanding of how a router operates at the network layer, the diagram on Figure 1.9 is, it depicts how this process operates. So, you should read this to kind of understand how packets are routed. And the process is very simple, right? A router examines packet's header, and then it refers that packet header to the routing table, and it does select the particular connections. Once it selects that connections, right, it gets it, and then it picks it up, it recaps the packet, put the packets in a queue for delivery. It's very simple. Just read this. So straightforward. This table is self-explanatory. If you intend to send this packet to a destination 172.16.10.5, right, which is here, right? So this is the process. It gets it, picks it up, right? The header looks at the destination, repackaged it, queue it for delivery. Bam, and that's it. Layer 4, transport layer. Before I proceed with the transport layer, I just want to call attention onto it. I mentioned earlier that from layer 4 to layer 7, they're referred to as the host layers. Some of the key things you should take note at this layer is services located in the transport layer segment and reassemble data from upper layer applications and unite data onto the same data stream. That's it. As well as data streams provide end-to-end data transport services and establish logical connection between the sending host and destination host on an internet network. Keep that in mind. Another responsibility of the transport layer, right? It's responsible for providing mechanism for multiplexing upper layer applications, sessions establishments, and teardown of visual circuits. It also hides details of any network dependent information from the higher layers by providing transparent data transfer. Also take note, it's responsible for data integrity. That's it. Keep that in mind. Very important as long as security is concerned. And that also comes with reliable data transport. Yep, reliable for providing reliable data transport. A connection-oriented communication, the TCP, which of course you're going to be seeing this down the road as we proceed. The TCP. And how is reliable data ensured, right? It is ensured when the segments that are delivered are acknowledged back to the sender upon their reception. If any segments that are not acknowledged are retransmitted, so it does retransmission as well. Also, if segments are sequenced back into their proper order upon arrival at their destination, so it rearrange the package and ensure that they are aligned, and then before it delivers it. So, and the last, provides a manageable data flow. Yep, which is maintained to avoid that congestion, overloading, and loss of any data. So, okay, layer 5, the session layer. The main purpose of the session layer can be likened to that of a mediator or a referee. Yeah, that just makes it very simple, right? So its central concern is dialogue control between devices or nodes. Its responsibility is that it coordinates communication between systems. So the session layer organizes their communication by offering 3 modes. So the 3 modes that does exist in this: the simplex, half duplex, and full duplex. So it's very simple. When we talk about simplex, half duplex, and full duplex, this is what we mean. Simplex simply means communication from a device just rolls one way, right? It doesn't take in, so if a device is communicating, it doesn't give a room for another device to respond at that same time. So it's going to. And the half duplex as well is that when a device communicates, it can't, but it doesn't give a room to do it simultaneously. But full duplex, right? Both devices can communicate at the same time simultaneously without any congestion or conflict. Yep. Another thing for you to take note here, the session layer, is that it splits up a communication session into 3 phases, right? And these are the phases. It establishes a connection. It does a data transfer, and then it releases the connection. So that's just very simple. The bunch of protocols that are involved or exist at this layer, and the table on figure 1.10 gives you details some of the session layer protocols and interfaces that are very common within its daily operation. So you've got the network file system, structure, query language, remote procedure call, Windows, Apple. You can just read this in order to get a thorough understanding of this concept. Here comes the presentation layer, layer 6. The presentation layer, from its name, right, it presents, or we say it displays data to the application layer. And it's also referred as a translator. The task associated to the presentation layer: data decompression, data compression, decompression, encryption, and decryption. Keep those in mind at the presentation layer. The table on figure 1.11 lays out presentation layer image graphic standards. So I'll tell some of us are familiar with standards like the JPEG, MPEG, very common. The last layer, which is the application layer, layer 7. A simple definition, right, is that the application layer provides a network interface for applications. So those are applications that have been presented using the presentation layer or display layer is being used at the application layer. So examples of application layers are like the email client or web browser. Also, although computer applications sometimes require only desktop resources, applications may unite communicating components from more than one network applications. For example, file transfers, email remote access, networking management, activities, client-server processes, and information locations. The diagram on figure 1.12, or the table on figure 1.12, presents a networking applications and that are defined. So you've got the World Wide Web and email gateways, just read that, get acquainted with it. Okay, let's jump into the OSI model. Contrast it with TCP/IP model. So the main thing here is just to be able to differentiate between the OSI model and the TCP/IP model. Some of the key things that makes the TCP/IP model differ from the OSI model. First, its look and feel. You can see. As you can see on that figure 1.13 that I mentioned or that I showed. Further, you should also take note that the OSI model was defined after the TCP/IP model was created, tested, and working. And also that the OSI model was created as a reference architecture first, and much of the specification that came from the work already done in the TCP/IP model. And as well, the stringent definition of the OSI model is much more detailed than in the TCP/IP model. Those are some of the things that you got to take note with the differentiation. And also that the OSI model layers are numbered, while the TCP/IP model layers are not numbered. However, they both have some similarities. For instance, they both describe how information is transmitted between the two devices across the network, and they both use the concept of encapsulation, in which data is packaged into a series of headers and transmitted. And just to emphasize again, OSI model layer is created as a reference, and it's got its layers are numbered, stringent definitions, and very detailed. While TCP/IP model layers do not have numbers, and they just define specifically for use with IT protocols. But like I said, they have some similarities, right? They do describe how information is transmitted, and they both use the concept of encapsulation. The diagram on figure 1.14, TCP/IP model doing encapsulation. So this is how TCP/IP encapsulates data. We've seen that with the OSI model. So this one is TCP/IP model. So it's got a source port, it's got a destination port, and that's the data, right? It fits it into the segment, and in that segment, right, it adds a source IP address and a destination IP address, and the protocol that's being used for that data transport. So talk about protocol here is pretty much like is a TCP transmission control protocol, and it's called a packet, right? And that's how I get into the frame. So the packet, you've got the source MAC address and the destination MAC address, and the Ether field, the Ethernet field, and the file check sequence. The diagram on figure 1.15 shows an OSI model doing encapsulation. Like I said, both models uses the concept of encapsulation. So this shows how it's done in TCP/IP, and on this one, it's how it's done in OSI model. In the descending order, right, from application down to data link. At the last stage, or at the top, it's called data. Down at the transport layer is referred to as segments, where it's got the segments. So when you have it as a data, right, it's got the upper layer data. It gets down to the transport layer, right, to talk about the TCP header and the upper layer data. So it adds a TCP header on there, and that data feeds, and then it adds an IP header. When it's getting down to the layer 2, right, we did talk about the logical link control header. It feeds onto the data and starts figuring out how to deliver it to the hardware. So that's when it's converted to ones and zeros at the physical layer, the values of numerical values of ones and zeros. So like I already mentioned, right, although both models, right, do share many details, the TCP/IP model is defined specifically for use with its protocols, and the OSI model was created to help define how a protocol model should be developed and function. Physical connections. Here we're going to be looking at trying to recognize physical connection, and we're going to deep dive into how to explain basic radio theory and then be able to distinguish between wireless technologies. Let's begin with data transmission. So when we talk about physical connections, right, it's when two hardwares are trying to communicate with each other, connect, and connection is that process of communicating. So I think that's the essence of data transmission. So, and to define data transmission here, it is a transfer of data from a source communications device to a destination communication device. So, and the data can be sent over channels such as copper wires, optical fibers, and wireless communication channels. And it's due to this that we're going to be looking at, those basic radio theories and those various wireless technologies. And the data that are sent over those various channels, right, copper wires, optical fibers, and wireless communication channels, can actually be sent as an electromagnetic signal, such as an electrical voltage. That's in a situation where you use an Ethernet cable, right? And it can also be sent such as a radio wave, right? Such as two wireless routers communicating with each other, or microwave, or an infrared signal. So infrared, we know that's an old technology, though it's still being used today, with other devices, but it's not as common as it used to be in the days. So something for us to note here is how a voice over an IP network is being transported. So here, when transporting voice over an IP network, analog voice signals first have to be converted to digital format so they can be encapsulated into IP packets. So, and the diagram on figure 1.16 illustrates a call from an analog phone which is connected to a router 1. You can see that, which is connected to an analog phone 2, which is connected to another router 2. The two routers are connected to an IP network, and you could see that, to an IP network. So this is to an IP network. The user at phone 1 speaks into the phone microphone. Says hello. And the phone sends its analog signal to the router 1. CFX. That's router 1. Router 1 converts the received analog signal to digital. It converts it to digital. See, that's the data. And then it puts an IP address on it and encapsulates the bits into IP packets. So that's the data. And then it puts a header, which is an IP address to the destination. So these IP packets are then sent to router 2, this router 2 over the internet, right? Over the IP network. When router 2 receives the IP packets carrying the digital voice, the router converts them back to analog signals. The analog signals are then sent to phone 2, where they are played by the phone speaker so that the user at phone 2 can hear the original speech. It's just basically simple, right? At the time when you make a phone call, it's an analog, and once it hits a router, it gets converted from an analog to digital just to facilitate that transmission, because that's the only way that those transmission protocols, like UDP in this case, can understand that data package. It needs to have an IP address in it before it hits the other router. And once it hits that router and it's going down to the layer 2, layer 1, right, it converts it back to analog, because that is the mode in which that physical device would understand and read that data. That's it. Some other things to kind of keep in mind here is just that process of be able to convert analog to digital and digital to analog. So it's very simple, right? First, it samples, and secondly, it does a quantization, and it encodes, and then it compresses. So that's when we're doing analog to digital, like in this case, right? It's analog to digital. It samples, it does the process of quantization, it encodes, and then it compresses. It compresses that package and it adds an IP address and sends it over. Once it receives it, what does it do? It decompresses and it decodes, and then it reconstructs it back to analog signal, and then it provides it to the phone. So, like I mentioned, that very first process of sampling, right? What is sampling? Is when signals are converted digital. So the analog signal is first sampled. Yep. So we already explained that process up there. So the diagrams in figure 1.17 illustrates two sampling situations. So in the first one, right, the analog signal is sampled with a too low sampling rate, resulting in imprecise information. And from the obtained palm signals, the original waveform can hardly be derived. In the second, a higher sampling rate is used, and the resulting palm signals represent the original waveform very well. So that's it. Read that. Quantization. You can read this just to kind of understand these various processes that are involved. You could go through that and just understand it for understanding's sake. Compresses. We already talked about that. So the table in figure 1.19 shows a codecs and bit rates and quality. So and how they're measured. So it says the mean opinion score, right? They can be measured by different means. So like the mean opinion score, and I used so. Let's get to wire and copper cables. Another means of data transmission here is the use of wire and copper cables. So yeah, Ethernet and coaxial cables are examples of wire and copper cables. We used an example. I did mention a case of plugging a Ethernet cable on a computer and it's hardwired to a router, right? And coaxials, and usually in our houses we get coaxial from the internet service provider. That's what connects into our walls and then provide internet to our routers before we could even use Ethernet cables. And in some houses, I think today we still use coaxial cable for TV, for satellite TV connection. So the diagram on figure 1.20 shows a 568A wiring, and that on the right shows 568B standard. So in orange colors, you can read that for better understanding. And on the bottom right, you have the crossover cables. You could read that. Those are standards of Ethernet cables out there that exist. You can read all this to get a thorough understanding of Ethernet cables and the various standards. One thing you have to keep in mind here is that the IEEE is responsible for naming standard guidelines. And get yourself acquainted with the various megabits that do exist. So another name for the Ethernet cable, we call them the RJ45. So RJ45. Fiber optics. Fiber optic cables are similar to a twisted pair cable because they are assemblies of multiple components. And, you should keep in mind here that fiber optic cables, they transmit data by sending light signals. Light signals, very important. That's how they carry data, by light signals. They can have multiple individual strands of fiber, each cable sending separate streams of light and therefore separate streams of data. Each strand of fiber is typically covered with a plastic coating to protect the actual glass strand, because they're usually out there in the wild. So this is how a fiber cable looks like. The fiber optic cables use different types of connectors. So the most typical connector today is the small LC connector. That's an image of it. Keep this image in your mind, keep it in your brain, memorize how it looks like. The LC connector. Figure 1.25 is an ST connector. 1.26 is an SC connector. So the most typical connector is the small LC connector. That's it. Followed by the ST connector in figure 1.25, and then you have the SC connector 1.26. Following at the expanded IE Ethernet 802.3 standard for fiber optics. Keep that in mind. Wireless connections. When it comes to various technologies, their classification, especially with radio communications, is dependent upon the distance that the communications must travel. Usage depends on distance. So in this case, a 5-foot range is probably used for person-to-person communications. Yep, that's too close. Yep. While 150-mile range is more likely to used for network-to-network exchanges. So look at this diagram here. The figure 1.27 shows network types by data rate and signal rate. So it just you could look at it. Narrowband wireless, it's very close, local, and right down. Yep, that's why we talked about those when we talk about narrowband. It means too close, right? Closer but a little bit high, infrared wireless. And 5G is right here, and that's where we are today. And then satellite wide, yep, that's why at both at the edges. So we've got the 5G, which is right top. It's not too wide, but satellite is at the edge because it's goes right into the entire wall. So it's everywhere. So we've got countries now putting satellite everywhere and trying to have access around the world and unlimited services. So okay, basic radio theory. We all know that a lot of devices today communicate, or the wireless devices, what they use is radio waves to send information. So a short definition for a radio wave here is an electromagnetic field that radiates from a sender. That's it. It propagates to a receiver, which receives its energy. Light is an example of electromagnetic energy. Something of importance here is just to kind of know, have an understanding of the different wave sizes and how it's expressed in meters. So, the diagram on figure 1.28 shows the wave spectrum, right? We've got the wireless networks and we've got all these rainbow colors, you can call them, right? Starting from, look at audio, radio, visible, X-ray, right? It's, yep. You've got from hertz, kilohertz, megahertz, gigahertz, trillion hertz. You can go forward. So the table on figure 1.29 just kind of shows us frequency and wavelength. One of the things that you have to understand with this frequency and wavelength is there is a direct relationship between the frequency of a signal and the wavelength. So when we talk about frequency here, we're talking about how often something occurs per minute of time, right? And wavelength is kind of like the distance the signal travels in 1 second. So how often it occurs and how far that thing runs, right? And that's the relationship. So that's frequency and wavelength. So in this case, the frequency is gonna be how these things are rolling left, right, up, down, and the wavelength is just a distance from point A to point B. Therefore, when a signal occurs once a second, it is 1 hertz. If it occurs 10 times, it becomes 10 hertz. If it occurs 1,000,000 times in a second, it becomes a megahertz. And 1,000,000,000 times a second, it becomes a gigahertz. Wavelength. Like I mentioned before, right? A wavelength is just simply a distance over which a wave shape repeats. So if that frequency, keeps going, repeats in that distance. On the other side, amplitude. It is another factor that affects how a wave is sent, is amplitude. Amplitude can be defined as the strength of the signal, so it's just the strength. So if it waves and it covers a distance, but how strong it is and what determines the strength, right? Figure 1.30 shows an amplitude. Therefore, when you look at this diagram, right, the amplitude here is just that distance between the higher and the lower crest of the circle. So, yep, that's it. Free path loss. The free path loss is simply defined as the loss in signal strength of a signal through free space. A radio wave emitted by an access point is radiated in the air. That's an example in free space. So, absorption. In the case of an absorption, is when a signal travels away from the access point, right? But then it doesn't lose that signal in the air, like in the case of the free path loss, but it does lose it through passing different types of material, like trying to go through a hot wall, right? That's where absorption comes in. So, reflection. Reflection is when a signal hits an obstacle. The reaction depends on the nature of the obstacle. Yep, you're right. So it just depends. In this case, we're talking about porous materials that absorbs part of the energy in rough materials. So they tend to reflect it with an angle equal to the one at which it was received. So, multipath. Another way that reflections affects wireless networks is through the phenomenon called multipath. So how does multipath works here? So when a signal is sent as a wave, one portion of the wave travels in a straight line from the sender to the receiver. This part is the main signal. Part of the same wave hits obstacle and is reflected, some of it towards the same receiver. So that's a multipath. Scattering. Reflection has to do with measure obstacles, but reflection also occurs in the air itself. That's what is called scattering. So when a signal, right, is reflected due to measure obstacles, as well as it's also impacted by the air itself. So, refraction. Refraction here is a phenomenon that occurs when a wave changes direction. Yeah, refraction. This change is in direction usually happens when a wave passes from one medium to another. Line of sight. In this case, as a signal travels in a straight line towards a receiver, it is received in good condition if there is a clear line of sight between the sender and the receiver. So if two devices are communicating and there isn't a wall in between or between those two devices, then that's what it's referred to a straight line towards a receiver, line of sight. Fresnel zone. The image on figure 1.31, radio line of sight. Yep. The radio line of sight, even when it matches the model of a straight line or a visual line of sight. Therefore, it is more than a simple line. So we just talked about a line of sight. So you have a line of sight, but then you have other lines that are more than a line of sight. To have an understanding about this Fresnel zone, right? Just think of the scenario for like a rugby ball or an American football. A sender and a receiver are at each end of the ball, and there is an imaginary line from one to the other, right? And calculating the Fresnel zone involves trying to determine the maximum radius of the ball. It is at its largest exactly midway between the ends. The arrow SSI and SNR the arrow SSI is just simply a received signal strength indicator, while the SNR is simply a signal to noise ratio. And you might want to focus on the signal to noise ratio to kind of understand when at what situation is it good or bad. Here that says a good signal to noise ratio depends on the received signal strength indicator. Yep. So, which means the received signal strength indicator indicates how much power is received, how much power is received. Therefore, which means if the received signal strength indicator is weak, it could have meant that the signal to noise ratio is low. However, a low signal to noise ratio is acceptable if that environment is quiet. But if the environment is noisy, then a higher signal noise ratio is needed in order for that signal to go through. Just take for instance, if you sit in a nightclub, right, and you're talking to somebody on the other side of the table, you gotta have to shout out loud for that person to hear you. So if you speak in tongue, if you speak at very low tune, right, the signal to noise ratio will be low because you're sending a very low signal compared to the noise within that nightclub. So that's just basically what it is. And if that tone is low, then the received signal strength indicator will be low because the receiver will not hear you. Wireless technologies. Keep in mind there are four main types of wireless technologies. Let's begin with wireless personal area network. It is a network that exists within a relatively small area, connecting electronic devices such as desktop computers, printers, scanners, fax machines, personal digital assistants, and network computers. To connect these devices, in the past required extensive cabling, connectors and adapters. The wireless personal area network, wireless communication standard, focuses on the following key issues: low power consumption, small size, its low cost. Those are its selling points. However, the requirements of the WPAN to limit power and size renders the Bluetooth not to be designed to extend further than about 20 feet, which is a huge limitation for this technology. Bluetooth is still being used today though, but you can't just go really too far from compared to other wireless technologies. WPANs are unlicensed, which means that users do not have to pay to use devices in the allowed frequency range. Wireless local area network. In contrast to WPANs, WLANs provide more robust wireless network connectivity over a local area of approximately 100 meters between an access point and associated clients. Its aim is not to connect one device to another, but to connect many devices to a network without the need for cables. In today's world, WLANs are based on the 802.11 standard, referred to as Wi-Fi networks. WLANs are more complex than WPANs because several users are typically expected to connect at the same time. WLANs are unlicensed, which means that users do not have to pay to use devices in the allowed frequency range. Wireless metro area network. A WMAN is a wireless communications network that covers a large geographic area, such as a city, a suburb. In this type of area, the wireless signal often provides a backbone, point-to-point, or point-to-multipoint. When this type of network is installed by a service provider, users often have to pay a fee to access it. Fees can be charged for anything from the right to use someone else's network to the right to use a specific frequency. Many of these links operate in the unlicensed band and are free to use. However, enterprise may still need a professional to install and maintain them and pay a fee for this service, which therefore means there is still a fee compared to the other ones. The downside of this freedom is that if anyone else wants to use the same frequency in the same area, both networks will compete for access to the RF medium, without it being possible to give priority to one or the other. The third Type of wireless technologies. Wireless wide area network. W1s provide connectivity over a wide geographic area. Usually, W1s are digital cellular networks used for mobile phones and data service and are operated by carriers, often referred to as mobile broadband. There are two types of W1 technologies. The GSM, which means Global System for Mobile Communications, and CDMA, which stands for Code Division Multiple Access. They're deployed worldwide. You can read through this to kind of follow through how this network has evolved over the years. In today's world, we talked about the 5G network. Wireless standards. Keep in mind that wireless networks use the industrial, scientific, and medical band, ISM. Therefore, being able to use a band that is range of frequencies does not mean that people can use it in any way they like. So there's some guidelines that we have to follow. There are key elements that must be defined when machines have to communicate with one another effectively. And these elements are defined by IEEE. They do include the type of modulation technique to use. They do define how a frame should be coded and what type of headers should be in the frame and what the physical transmission mechanism should be. The table in figure 130.32 lays down the protocol specification for wireless devices. You can go through that and get acquainted with those protocol specifications. The table on figure 1.33 lays down IEEE current and active committees and standards. You can go through that and get acquainted with it. Then comes the Wi-Fi Alliance. IEEE sets those specifications, but they do not have the power to require an enterprise to implement certain protocols in its product. Therefore, the Wi-Fi Alliance was created to solve the compatibility issue. It came up, develops rigorous tests, and conducts Wi-Fi certification of wireless devices that implement the various wireless IEEE 802.11 specifications. It was created in 2000. Besides that, there are other regulatory bodies. The IEEE defines layer 1 and 2 protocols, and the Wi-Fi Alliance ensures its compatibility. However, other countries, they also have their own rules about the type of radio signals that can be sent over each frequency and what signal strength can be used. The US FCC determines the frequencies and transmission power levels that may be used. In Europe and some other countries, they also have their own rules and regulations or specifications. The determined by the European Telecommunication Standards Institute. Japan as well has its own specification defined by the Ministry of Communication. Australia as well has regulations that are set by the Australian Communication and Media Authority. And it does reports directly to the Minister of Communications within the federal government. Thank you for watching this course, and I hope it helps. You can go to the knowledge check and kind of test and see if you actually got something out of this. Good luck.